Hello, everyone. This is another exciting episode of the Interactive International Technical Talk by ISSMGE. I launched this initiative. It's gaining momentum. We are at episode number 28, I think. This time, a very exciting topic with wonderful presenters. I'm going to share my screen. So thank you for having with us from TC102 about site characterization, Professor Jason DeJong from University of California in Davis. He's going to give us an overview of the technical committee activities and what they do around the world. Dr. José Estaire from Laboratoire Geotécnica in Madrid, CEDEX, Spain. Henry, you're active consultant with WSP USA, originally from Ghana. Welcome. And Julia, currently in Germany. She's a doctor at the Institute of Geotechnics in Freiburg University, Mining and Technology. Welcome all. Can't wait to see what you're going to tell us, and please be interactive. I created this interactive talk to bring together experts and renowned people and young engineers from all over the world. And we're going to cover today guidance regarding determination of property and design values. We may talk more about the Eurocode, and I leave the floor to you, to Jason, to start first. So I will stop sharing. Jason, the floor is yours.
Well, thank you. It's a pleasure to be able to host this, to be able to organize this on behalf of TC102, the Site Characterization Committee. We're going to talk, as was mentioned, about determination of ground property design values, and this is actually stemming from a lot of the leadership and the early advancements in Eurocode 7, and now the second generation of Eurocode 7. So the selection of ground properties is obviously a critical part in what we do. It's an end product in a way. And so that's why we selected it. It's not specific or only applicable in Europe. It's really guidance that's applicable at any project site anywhere around the world. And so let's think about it in that context as we go forward. I'm just going to spend a couple of minutes about our committee. So the title is Site Characterization. Of our committee. This was recently changed from ground property characterization from in situ tests. And this comes from a broad recognition by the committee that in situ investigation tools used in present date, state of the art, state of practice is really, really, really broad. It now includes the conventional drilling and sampling and in situ work, but also geophysics, remote sensing, geologic mapping, geostatistical modeling, ground models, and selection of representative properties, hence this meeting and this IITT today. Our mission, if you wanted to sum it up
You
as
brought you
TC102,
brought to yourself way more work now.
what was
Good.
that?
You brought to yourself way more load, way more work. Good
Yeah,
luck. That's very, very important step. Thank you
yeah,
for doing it.
we got to add those pieces in. So we're really trying to promote both the use, but also improve the interpretation of site characterization methods, facilitate interaction between the academy and industry, and really try to push and provide access out into industry. And so I'm the chair of that committee. Paolo Monaco out of Italy is the vice chair. Marcos is a secretary. We have a number of members, 83, but always looking for more people who are willing and interested in being actively involved with our variety of activities. Those are numerous, but I would say our committee maybe is highlighted with respect to the number of meetings that we help organize and host. And so just a snapshot of some of those that are coming up. We've had two recently in the past year. There's a measurement while drilling conference. That's an online conference in a couple of weeks. Obviously, we're participating in the ICSMGE next June in Vienna. There's an in situ conference in Bali later next year. The following year is CPT 27 in Vancouver, and the 8th International Conference of the ISC is going to be in Cape Town, South Africa in 2028. So there's a number of activities that we provide opportunities for academics and for industry to come together, to share ideas and collectively help advance the field. Just wanted to provide a comment and context about the selection of design values. Really, it's a critical component of the development of a project-specific site model that we use that's developed based off of site characterization tools. We need to understand the geologic formation process. We want to reflect best estimate values as well as a broad range, and that's what we'll be talking about. And it needs to be a transparent process that's easily reviewable. So I like this figure from a project site where they're building an embankment dam. And you can see here a vertical cut of about 30 meters. And what's beautiful about this is you can see there's all these thin layers and these fingerings in all these different places of all these different soil types. And if we did one sounding over on the right-hand side and we did another sounding over on the left-hand side, you know, maybe we would encounter the same layer, perhaps this location over here on the left and over here on the right, and we might assume that those were connected if we couldn't see in between. But in fact, they're not. And in fact, the subsurface is tremendously variable due to its depositional process. And so the question becomes, if this is what we're trying to design for, but we have very, very limited data, how do we do that? That's really the underlying question, the underlying theme about what we're trying to get a hold of and what we're trying to think about. So hopefully that sets the context a little bit. I'll pass it over to Jose and feel free to take it from here as we begin to delve into the process to systematically select design values.
Okay, thank you, Jason, for this opportunity to share my experience with Eurocode. Let me share.
Jason, that was very short and very powerful.
I have more
and
slides.
Scary at the same time with the section view.
That's the reality.
How much we don't know.
We only sample.
It's the first time, yeah, somebody shows what we don't know instead of showing what we know. I like it.
The question is, how much do we not know? And we actually are over-optimistic, I think, in us understanding the subsurface. The mystery is much greater.
Well, so Julia and me are going to show you what says Eurocode 7, the second generation of Eurocode 7 about this. So good afternoon, and my presentation is about the ground property characterization according to the second generation of Eurocode 7. And let me begin talking about the second line of the title, second generation of Eurocodes. Eurocodes, for those that don't know, are a suite of 13 documents that establishes principles and requirements for safety, serviceability, robustness, and durability for the design of buildings and civil engineering works. Among these documents, Eurocode 7 is the one devoted to geotechnical design. Second generation of Eurocode 7 has 3 parts. Part 1 sets the general rules for geotechnical structures, for the design and verification of geotechnical structures. Part 2, devoted to the ground properties, gives provisions and guidance for planning ground investigations and set rules for determining the ground properties, mainly based on field investigations and laboratory tests. And Part 3, geotechnical structures, provides specific rules for specific geotechnical structures, such as, for instance, foundations, retaining structures, or even some new topic about ground improvement works. Now, let's focus our attention on Part 1, since part of its content is directly related to the topic of this seminar. In the following slides, we are digging in such Part 1 to find the specific contents we want to explain. So let's begin with Part 1 and its table of content, in which we can see clause 4, basis of design, devoted to the principles of this design. And going on, section 4.3, basic variables, and finally we arrive at point 4.3.2, material and product properties, where we can find these paragraphs that describe different concepts about ground properties, representative values, characteristic values, and nominal values, which constitute the main topic of both Julia's and my presentations. But, however, I don't want to lose the opportunity to also to show you or to present you this GRC guideline, determination of representative values from derived values to verify limit states according to Eurocode 7, since it explains many of the concepts that Julia and me are going to develop during our presentations. It's a guideline edited by GRC, drafted by a group of people, led by me, and where Julia plays a very important role. It can be freely downloaded from the GRC webpage, and you can see here its table of content. And here the relation between the content of this guideline with the previous point I have mentioned. And I have added also Annex A from Part 1 in Eurocode 7, characteristic value determination procedure, because it's very important for what Julia is going to explain later. So now let's go to the core. Yes?
Yeah, sorry to interrupt, but this is ongoing work or it's finalized? So
no, it's finalized.
We have a final version of Eurocode, so
yes.
people can open the link and see, use it for guidance.
Yes, this guideline was finalized at the beginning of this year, after almost 2 years of work in this task group, and now is finalized. And I think it is very valuable to understand, to better understand what we are going to explain in these 10 minutes plus 10 minutes presentations of today. Yeah.
And was it done in an electronic format, application, or just a document PDF, just to tell everyone?
Yeah, it's a PDF document, downloaded from, it's a PDF. Yeah.
We will let ChatGPT go look at.
Yes, to make a summary. To make a summary of that. Yes. Okay.
Good. Yeah. Thank you.
So before entering in the core of my presentation, I want to show you this little flowchart, because it's my interpretation of what the process, the different tasks in the process of design of the technical structure according to what Eurocode 7 says. According to my understanding or my interpretation, this process has 5 main tasks. Task 1, reliability and assessment and management, ground investigation and modeling, design verification, design implementation during execution, and reporting. Something very related with what Jason has said previously about the transparency of all the process. All these tasks has its own report in which the designer have to develop all the work we have done during the design. What we are talking about today is represent the last step of this task 2 and the first step of this design 3 design verification. So it's in the middle of these 2 tasks. That's why I put it here only to frame the activities. And let me begin by reading the first paragraph or the first point that of the points I previously presented, because I think it's a good summary of what we are talking about. Representative values of ground properties, and now we say why do we need those representative values to be used in limit state verifications shall be determined from derived values presented in the ground investigation report. That means that according to Eurocode 7, a value should follow a path from the moment in which it's taken during the ground investigation activities to the moment in which the designer use that value in the design and verification of limit states. And this path can be summarized graphically in this flowchart, which goes from derived to representative values that goes from ground investigation to design, passing through this other concept that I'm going to explain. But before explaining this flowchart, I also want to read the note. The representative value refers to a particular ground property of a single geotechnical unit. Thinking this, for instance, slope, in which we have identified 2 or 3 layers, let's say geotechnical unit, in terms of with the vocabulary of Eurocode 7. And if we want to perform an overall stability analysis, we need at least the cohesion, friction angle, and the weight density of each of these layers. Each of these ground properties are ground properties of each of the geotechnical units. So now let's go to the flow chart, to the upper begin with the upper part. As usually in all the geotechnical works, we begin with the ground investigation. According to Eurocode 7, ground investigation is composed of 4 main tasks or activities: depth study, site inspection, design investigation, in other words, in situ and laboratory test, and monitoring and observation. In each of these different activities, we can obtain some different values, which are termed for this presentation and historical, assessed, test, or monitor, or measure, or even monitor values. And now, applying some or using some theory, correlation, empiricism, or back analysis, we transform these values into derived values. To better understand this concept, think in a direct shear test. These curves are, let's say, the test values, the curves that relate the horizontal displacement with the shear stress. And if we apply the molecular model, we obtain a value of cohesion and a value of friction angle. These values are the derived values. That's why we have used some theory. So now, thinking again in the example before, example, imagine that we have 7 or 8 direct shear tests. So for that case, we have 7 or 8 values of cohesion and friction angle. These are the set of derived values that appear here in the middle of or in the upper part of the flow chart. The next step is to determine the determination of the representative value. Here there are some ideas to take into account by the designer during this process about the knowledge, the pre-existing knowledge, about the quality and quantity of the data, and about also very important about the spatial variability. And also looking at that right part, the ratio between the spatial variability and the length of the surface is an indication of what is the value that affects the limit state, as Julia is going to explain later. This is two groups of ideas are very important in the determination of the representative values. So now, coming back to our set of derived values, the designers have 2 paths to obtain or to determine the representative value. One is using statistics as a tool to calculate a value, which is termed as characteristic value, to distinguish it from the other path, to the other way, in which the designers, instead of using statistics, are going to use their engineering judgment as a tool to select. In this case, is more subjective. It's a more subjective process than this one. That's why we have preferred to use the verb select instead of determine or calculate. The designers can also use both. That is what is recommended in that DRC document. But in this moment, the designer has either the characteristic or the nominal or both, and they have is in the hands the decision to consider the representative value, either the characteristic or the nominal. So representative value is determined through these two ways or paths. And now the last step is to use these representative values in the design process, in the limit state verifications. For the limit state verifications, according to Eurocode 7, there are two approaches. In the material factor approach, the designers is going to calculate the resistance using the design value. The design value is the representative value divided by a partial factor of materials. While in the resistance factor approach, the resistance is calculated using directly the representative value, and then the calculated resistance is divided by a partial factor on resistance. If we are in the serviceability limit states, we can use directly we use the design value, but in these cases, the material factor is equal to 1. So this is the end of the process that is set, or the procedure that is set in Eurocode 7 to determine the representative value and to use it in the design process.
Jose, can I
Yes.
just ask a couple questions?
Yes.
This flow chart on the left is really good. If you go back up a couple slides to where it covers the top part. Yeah, I'm curious in the guidance if there is clear delineation and guidance regarding separation of what is factually generated in the laboratory in the field versus the point where we really start exercising judgment, right? And so in the case and trying to reconcile values. So I follow through most of this, and you have to use some methodology to interpret the data. Let's say, as you showed, going from a shear test to CFE. If you're using CPT data, let's say, then you can go through to QT, and that is a factual, if you will, mechanical equipment-based process of data reduction. But then we have a choice, a step, in let's say, selecting strength values for a clay layer. And now I have several different correlations. And so at that point in time, when the engineers start selecting, they're starting to insert judgment now, because they're choosing between different correlations, let's say, to try to estimate strength from. And so I find, as a reviewer of, and particularly on larger projects, it can be very important to separate where the facts by themselves kind of end, and then where you start inserting this judgment and documentation of the judgment there, of that judgment and the justification behind it. So in peer review, or if every 5 or 10 years a critical structure has to be re-reviewed, you have great transparency of how that works. So I'm curious about your thoughts with respect to this in particular.
Yeah, well, you are touching a very important topic that many discussions about this. Actually, let me show you some. Well, I mean, some ideas. First of all, although it's not very clear, I mean, that's here. The grounding, this let's say upper part of the flow chart is very related with part 2 of Eurocode 7. It's the ground investigation. And when we jump from part 2 to part 1, it's where it begins, let's say, that engineering judgment. Although, as you mentioned, in the determination of the calculation of the derived values, there are also some theories or correlations used. Some countries, I mean, and these, according to another idea, according to this paragraph, see that derived values are presented in the geotechnical investigation report. the geotechnical investigation report in some countries is now Eurocode 7 opens the possibility that for some countries the geotechnical investigation report is factual, but for other countries is going it should have some interpretation. So it's not clear. Okay. That's one, and another, and that's my last thought about this. This is very important that in Eurocode 7 there is a table that it's measures to validate the content of the geotechnical investigation report. There is this table. It's it's a signal or a sign that Eurocode 7 sends to the designers to say, in the moment you validate all the values, all the information that is contained in the geotechnical investigation report, your responsibility begins.
Yes, okay. I like that.
It's clear that in some moment in each country that moment begins in a different moment in the process, but it's clear that according to Eurocode 7, in the moment that designer validates that report, the responsibility is in the hands of the designer. And also, if the designer does not validate that, it can go up and to, let's say, rethink or recalculate these values for them or for the designer to be sure they like what are the derived values.
Yeah, and that makes sense too, because oftentimes for critical design parameters, we want multiple types of measurements to estimate a particular parameter, and then we have to reconcile those differences. And when we try to reconcile those differences, again, there's engineering judgment in that process. Well, oh, go ahead.
Sorry, actually, Julia is going to talk about this, and also let me in this guideline in chapter 5. Well, we have titled special topics, but perhaps it's not so special. There is some section about how to determine the representative values when there are different sources of information.
Yeah, nice. Okay, thank you.
We need many hours or many days to go through the details.
Yeah,
I know. This is excellent, though. This is guidance. This is guidance anyone can use anywhere.
Yeah. So this is a
José,
summary.
Is there in the guidance some recommendation to store the data in data format for future use, like AGS or other data format? Does it mention anything about that?
No, it's not mentioned in this guideline. There is another. This is one of a set of 4 guidelines, and another guideline about it's called ground modeling. In that guideline, there are some ideas about this. What you are saying.
Let's keep going. Thank you.
Thank you, Jose.
Thank you.
Go ahead.
I stop sharing.
Okay, so I guess it's on me to share now.
The floor is yours, Julia.
All you need to do is teach us how to do all of it.
That's it.
Yeah, I guess we just dive a little bit deeper into the Eurocode 7 and part 1. So as Jose already introduced, there are different types of values in the Eurocode 7 part 1, and he already introduced the representative value, which is used in ultimate and serviceability limit state, and it's from the ground investigation report. And then we have this nominal value, which is a value that is fixed on a non-statistical basis. So that's the engineering judgment value, as you may remember. And then it should be selected as a cautious estimate of the average inferior or superior value. But what's more interesting for us in the next few minutes is the characteristic value. And this is derived based on a statistical determination of the value of a ground property. Now we're going to check how the statistics look like. So what should we do when we want to determine our characteristic value and use statistics? This is the main equation we have for independent derived values. So now we get our values from the CPT data that are already transformed, for instance, to the friction angle, but also data from shear tests. And then we can calculate the characteristic value by using the mean value of all our ground properties. And then we have something that's called a statistical coefficient. And this is the coefficient of variation, which is the standard deviation divided by the mean of our ground property. And then Eurocode 7 makes the things, I wouldn't say complicated, but you have to understand it once. So there are different types of estimates, and they're very much related to the averaging of the ground properties, but we will come to that in a minute. So we have something that's called a type A estimate, and this is basically the estimate of a mean value. So it's a 5% fractile of the mean value, actually. And it's derived by this kind of equation. And then we have something called a type B estimate. And this is the estimate of a lower 5% or upper 95% fractile value. It's derived by this kind of equation. And then we have something that's in between. So it's something between the mean and the 5% fractile usually. And there we have a very specific value, which is the large gamma squared. And this is a factor that accounts for the spatial averaging. Then we have also two different cases. So we have case 1 and case 3, and they reflect our knowledge on the coefficient of variation. So the Vx known and Vx assumed means that we have some information on our variability in the ground, whereas the case 2 means Vx unknown, so no knowledge on the variability of the ground. And in this case, we use the student T distribution for the Kn value instead of a Gaussian distribution, which is the student T distribution is a little bit more conservative. So it gives you, in the end, lower characteristic values. So we have the different values as mentioned, and then always the number of samples or the number of derived values that needs to be included in our definition. So to have it on the slide and to show what it actually means, so when we have lower representative values, this is our distribution of the ground properties. And then when we have a 5% fractile value, so a lower value, it means that 95% of our values are larger than the characteristic value we determine with our equation. And if we have an upper representative value or characteristic value, then 95% of our values are smaller than our characteristic value. And then we have this spatial averaging thing. So when we have a type A estimate, it means that we are calculating the mean. And for calculating the mean, we need to have a lot of spatial averaging. So the ground properties on our failure surface, as we can see here with the slope, they need to average out over the failure surface. So we get closer to the mean and our distribution gets smaller. So this is the type A estimate. And then we have this type B estimate where we estimate the 5% fractiles. And this is the pile example where at the bottom of the pile, there's only the tip of the pile and there's not really a lot of averaging of the ground properties. So in this case, we would use the type B estimate. And then we have the intermediate case, which is only described in the TC3, in the guideline, actually, in the guideline José just introduced by TC1. And the type C estimate means that we do have spatial averaging, but it's not like a full spatial averaging that it converges to the mean value. And this is, for instance, for strip foundations or foundations at all, where the type C estimate could be interesting. So then we were also already talking a little bit about data, and the Eurocode itself, it says that when available data are considered sufficient to establish the characteristic value, then the representative value should be determined from this formula. So basically what it means is that if the engineer considers that he or she has a sufficient databases, then the characteristic value is kind of preferred. But the Eurocode doesn't say what does sufficient mean. So you have to decide on your own what sufficient data really, what does it mean for you? And the guideline Jose introduced a few minutes ago, it tries to explain what sufficient mean, and it also says there's no unique way to select the minimum number of samples, because it depends very much on your application and also on the data. When you have a lot of variability in your data, you need more samples than when you have only little variability, and also when you have the geotechnical structure in the higher geotechnical category, you also need to have more data than in the lower geotechnical category. But the sufficient, it doesn't only relate, and because this is what we usually would expect, that it's related to the number of samples, but it's also related to the data quality. If you have triaxial tests, for instance, compared to CPT data, then they are of higher quality, and you would it would be easier perhaps for you to define the characteristic value based on the triaxial test data. What also needs to be mentioned is that by adopting all the measures that are set out in Eurocode 7, and that applies to all 3 parts, the level of reliability that is required by the Eurocode 0, it will be achieved. So as long as you follow the guidance, the level of reliability will be achieved. And there's like a rule of thumb: the number of samples, when your number of samples increases, then the level of confidence in your representative value, of course, also increases. So the more samples you have, the better, of course. The guideline itself, it tries to give you a little bit of guidance when it comes to the number of samples that is required. And there are different criteria for selecting the minimum number of samples. And as you can see, there are quite a lot of different criteria. You don't have to look through all of them, but the engineer in the end has to decide which criteria would be applicable to his or her application. And then you can see there are also different numbers of samples there. Like there's a minimum, but there can be up to 12 samples or even 33 samples that are required to achieve the target that was looked into for this specific criterion. But the guideline, it also provides examples for this kind of criteria, so you can check how it would work with your use case. Then there are also other topics when it comes to the selection of characteristic values. The equation we've seen at the introduction, it was only for independent ground properties, but usually what we have are perhaps dependent, depth-dependent or dependent ground properties. And then you have to select your characteristic value as a trend function usually. And the guideline also tries to explain how this will work and how you can estimate the uncertainty in your, how you can still define a characteristic value with the uncertainty in your data based on the equations that are written here. So you also get the mean value trend. So this would be our type A estimate. And then you get the 5% or 95% fractile value, which is our type B estimate. And because I brought a lot of numbers, it might be a little bit difficult to pull up all of the numbers. There's a small example. So we tried it in Germany, actually. It was also a publication with colleagues and me. And we had data from an engineering office. And they have a number of shear tests. So direct shear tests, 8. So not a lot, but considering, 8 shear tests are still a lot when it comes to geotechnical engineering, I would say. And they use the data for the planning of a flood retention basin. And what we assume for our calculations is that we have a type A estimate because they kind of rearranged and restructured the soil when they built the basin. So we assumed there was no correlation structure. And as you can see, so we quickly move to the results. We have our different cases, so case 1 and case 2 and case 3, so with the different Vx known. And every time we just have to calculate the Kn value with the equations in the table I've shown you. And then depending on whether we know the Vx or we have to assume it based on tables. So in the Eurocode, in Annex A, you can find tables where they give you a rough guidance on the Vx you could expect for your soil type. It's actually not related on the soil type, but at least on the ground property. So you can look it up or you can calculate it on the data as it is done here. And as you can see, the different cases, they give us slightly different results regarding the characteristic value. And the most conservative is the Vx assumed case. Say this is case 3. And the most optimistic one is the case 1 estimate, where we know our Vx and we calculate the standard deviation from the data. But all in all, they're not too far away from each, like they're still really close. So it seems to, within an engineering judgment, it seems to be a good estimate for now. And we also compared it actually to the nominal values that were given by the engineers and provided for the design. And they were, the values we calculated, they were quite close to the nominal values that were provided by the consultant. And what you also can see, actually, because we only have 8 samples, it doesn't look like a normal distribution, but we still use the normal, the Gaussian, the student T distribution. But the Eurocode assumes, so we assume an underlying Gaussian distribution, and this could be in some cases not the best choice, but for the friction angle, it should be fine. When we increase the number of samples, it should come up to the Gaussian distribution. So let's recapture a few things. So the nominal values, as introduced at the beginning, they usually reflect many years of practical experience, but and they are also determined on a limited number of samples. So usually we can deal quite well due to our experience with the uncertainty in the ground. But the statistical methods, the new Eurocode, like the 2nd generation introduces, they allow for a more explicit quantification of uncertainty. And they also, what they make understandable is that sample size actually matters. So the more samples you have, the better your estimate. And you can also estimate how useful additional data can be, how it can help you to reduce the uncertainty in your data set. And there are different documents supporting the determination of representative values. They're available on European level, which are the JRC reports, but often, as far as I know, there are also national documents that are currently worked on. So there will be a lot of guidance on how to select representative values. And I also have to add, because now I just touched a few topics, as Jose already said, the guideline, it has more information on depth and stress dependent properties, and it also shows how you can combine data from different sources in terms of a nominal value, but also in terms of characteristic and nominal values. So it's really worth having a look into it to get some ideas on how to combine data as well. And finally, I also have to acknowledge the guys who provided data for the example. Yeah, because it's always a bit difficult to find someone with a lot of good data.
Thank you, Julia.
Thank you. Thank you. I want to link the photograph that Jason, you have shown previously with these little fingers of different layers, with the ideas that that Julia has shown about these 2 types of estimation, type A and type B, because depending on what you are calculating, or depending on the limit state you are verifying, you must select one or the other, depending on, let's say, the volume of the failure surface you are assuming. And that's and that, I think it's a way to answer what you have mentioned during your presentation. How to do with this geology, very, very difficult geology with different fingers. So it's a way to say understand that the geology is difficult, and there are some ways to address that problem.
Let me say quickly what I would do, and then maybe a door to discussion before give the floor to Henry. In a remote area in Nigeria, when I'm faced with an embankment of a new highway and there isn't enough data, I also run and I don't know if it's in Eurocode 7 recommendation, sensitivity analyses to see how much the data I am looking for affects the results. And when I find that one item is very important, let's say consolidation behavior, I ask for, because of time, get for me this kind of data so it becomes a known Vx. Is there some, I saw the loop in the main chart, but is it mentioned somewhere that we should run sensitivity analysis instead of wasting time on a value that does not affect the final result of a designer? Some guidance there? Question is for Jose or Julia or whoever.
Yeah, at least I know in Germany, our additional guideline, we also recommend to do a sensitivity analysis before you calculate the characteristic value. So yeah, there's guidance also on this.
But it's not in the Eurocode. The Eurocode is basic guidance for obtaining characteristic of the soil, different values. Okay.
Yeah, but I mean, most of the information now you've seen in Jose and my talk, they are not in the Eurocode itself, you know, it's all in the guidelines. So the Eurocode is a very clearly written document, but it does not provide a lot of explanation.
I mean,
Jason,
following on that comment, you know, one of the important things early on, I think, is knowing and identifying your performance mechanisms. What do you expect? What mechanisms do you expect to govern performance? And then if things work out, you have appropriately forecasted what those could be, identified what the properties are, and it works out. And checking, okay, which parameters are really governing, really defining things. Two other comments, Julia. That was a great presentation. One is you said properties dependent with depth, and that was the slide. I see with in situ data in particular for the TC102, people will be interested in distributions of cone data or of SPT data or of strength data. But all three of those really have to have normalization by vertical overburden stress.
Yeah.
It's not depth. It's not depth.
No, it's not depth. It's called
vertical overburden stress.
Stress-dependent properties. I think this is what it is called in the guideline.
And with all three of those, they all have different normalization mechanisms to normalize the overburden stress. They're not all just proportional, and so it's something to take a look at. And then the last thing was a question. In addition to having greater quantity of data, there's also balancing that with the spatial distribution, right? And we talk in one of our classes, if you've been a practicing engineer for 30 years and you have 30 years, if you have 1 year of experience 30 times versus 30 years of experience, that's a different thing. So if I have 30 measurements from the same sample, I'm not any really better off than having 1 or 2 tests from that sample.
Good analogy.
But if I have 30 samples across my site, I have my spatial coverage across my critical layer, and I have sample from all those. Oh, now that's 30 samples.
I mean, all the number of samples always refers to just one layer. So we're always looking into one geotechnical unit where you have to have the number of samples or the number of derived values.
But it's across laterally that whole layer. It's not just at one location, yeah?
No. And then you have something that's called spatial variability, and this is also accounted for in the Eurocode and the characteristic value. So this really shouldn't matter, because this basically it comes back to your spatial averaging thing.
Yep. Awesome. That's very helpful.
Jason, you reminded me, experience is the number of problems you've seen in those years, not the number of years.
If you see the same problem every year, then you're not really learning.
Yeah.
Well, good.
Henry, are you ready? Sorry, we squished you. I know you have to go back. You're at the lunch break.
No problem. I'll try to fix everything.
Floor is yours.
Yeah.
Play mode.
Oh, hello. As earlier introduced, my name is Henry Asamany. I'm a consultant with WSP. Before joining WSP, I worked in Ghana as an engineer. And in Ghana, one of the very popular tests that we regularly use is the dynamic cone penetrometer test. Well, since my time here, it hasn't been a very popular test. I've never actually even used it since I got here anyway. But in context of Ghana and the way it's set up, it's a test that has proven to be quite useful and very handy for us. And we use it in various things, as I would show in the subsequent slides. I'll also talk about how we use the DCPT to determine this representative values and move those values to the points where we use it in analysis, maybe to calculate our bearing capacity and then settlement. So here I just have a little sketch of the DCP and how it operates using a standard hammer that drops over a specified distance, and the number of blows that is required to drive the rod or the cone into the ground over that specified distance gives the end value, similar to the SPT, but this is a lightweight one. In Ghana, there are two main types that are typically used. We have the dual hammer, which is the 4.6 and then the 8 kg. And we typically use those for roads, pavements, and cases where we need greater resolution or sensitivity, or the soil is more sensitive. We also have the 10 kg, which we call, or popularly called, the DIN. That's more used towards shallow foundation design due to the heavier hammer and its ability to go to deeper depths. We are able to drive it up to depths of up to 8 feet below the surface. Now, the reasons why maybe the DCP is quite popular and not maybe an SPT or some other type of testing. Generally, the DCP is very cheap or cost-effective means of measuring ground properties as compared to other tests, maybe as you would run the SPT or even taking samples and running those samples in the laboratory. So most people would typically tend to go towards the SPT. Also, the soil types we have are essentially ideal for using this equipment. Generally, as you can see in the image on your left, it's a lateritic formation that is mainly consisting of sands with various compositions of silt, clay in there. And also, most of the projects that are run in my country, we are typically smaller scale projects, and this gives the rise to the popularity the DCP sees. And then finally, a lot of work has been done by our universities to be able to generate or create correlations that are both soil specific and location specific, that allow you to move the measured data from the DCP to represent to data that you can use for design. And I've listed some of the very popular publications that have done exactly that. So mainly, as I said earlier, for shallow foundation design, pavement design, and field compaction control, here a group of technicians are using it to assess the degree of compaction in the field, as you can see. So I have a flow chart here of how we move from measured field values to using the values that we generate for our checks, bearing capacity and then settlement. So typically we start from measuring field values, and it's important that you understand the type of foundation or the job you are running and choose the right DCP tool. We want depth, the tool to go to depths greater than a couple of feet greater than the depth or the width of the foundations we are designing. So it's very important that you select the type of DCP that has the depth range that is applicable for what you are doing. The second stage has to do with deriving the subsurface properties, where we use the empirical correlations that have been developed by our universities to move the measured values into either CBR, modulus, friction angle, and then use those for design. And the third step has to do with, in Ghana mostly, yes, it's more of a conservative selection of the the representative value. Not there's a lot of, because the DCP doesn't bring out physical samples for you to actually see what's present there, and it doesn't take into consideration the moisture content as well as a lot of other reasons. Mostly we tend to stick with a conservative or use a nominal approach to selection of that representative value to use in design. And then we apply these factors and then use those values for the final checks and design. So to summarize, I've tried to keep it really short. To summarize and why it's very popular, it's due to our soils, the cost associated with running the DCP in our setting, and the flexibility it gives engineers to be able to quickly mobilize to sites at lower cost. And then there's a lot of work that has been done that has various correlations that allow us to move the measured field values from that point all the way to using it for design. I also wanted to list some limitations that we do have when we use the DCP in design. The first has to do with the limited depth range that it provides. So for certain types of foundations, it may not necessarily be ideal because the influence area exceeds what the DCP, the data the DCP can collect. And also, depending on the choice of DCP and then the soil properties, you may not be able to adequately determine what the composition of the soil is. It just gives you some mechanical properties associated with the soil at that point. And it doesn't provide a good ground model unless you pair it with other tests that allow you to excavate into the soil. And even with those, they are limited because most of the time you use manual labor to do that. Then also the strong dependency on the soil properties also influences the DCP. So in sometimes the moisture content plays a role and is able to either increase or reduce the skin friction experienced. So these are some of the references on various works that have been done, and you can find correlations to move the results from the dynamic cone penetrometer and help you for design. Yeah.
Henry, thank you so much. You brought another example of one specific test. You put a spice to this presentation with photo from Ghana. I really like it. Well, in summary, my summary, the more data you use is better. So with the DCPT, you can get a lot of data and reduce this variability that they were talking about, but also do more tests, predict the behavior, mode of failure, run sensitivity analysis. I'm giving recommendations to our viewers. And best wishes always. I wonder if you want to finalize, Jason, some final comments. Thank you all for being with us. This is a great episode. I'm so excited. It will be uh, aired and launched in the coming week or two, but you will get a notice. And many, many thanks. Jason, you want to say something?
No, I mean, thank you all. I think one of the big challenges for TC102 is we spend a lot of time talking about and getting very excited about equipment and then generating factual data. But that's not what practicing engineers use. Practicing engineers have to go from there through all these steps of interpretation, synthesis, integration, and then really simplification, because none of our numerical tools, no matter how advanced, can capture the beauty of spatial variability that the subsurface has, right? That cannot be captured. And so the responsibility of the engineer, as you said, Jose, that's when responsibility really kicks in, when you start making the decisions to simplify not just the properties, but the entire stratigraphy and the loading mechanism and everything else. That's really where we earn our money, so to speak, as geotechnical engineers. And so that's what we are hoping this combination of presentations would show and we could talk about. And I think that's happened. So on behalf of TC102, thanks a lot. It's fun.
Thank you.
Any more comments, Jose?
No, for me, it has been a pleasure to be here and to show you what we have been working on during this last year, during drafting Eurocode 7. And I think it's a good tool, but it must be used for many people. Thank you.
Yeah, it's useful for everyone. Thank you all.
You reminded me to give a quick idea. Well, it's still recorded, but it's okay. It's for everyone. We are launching in the Heritage Time Capsule, the physical time capsule. I don't know if you received those. What do you think we should place in that capsule, which will be a closet, showing the future generation what we've been doing in the 100 years? We came a long way in geotechnical engineering, and now what Jason is saying, we still have a long way. So that time capsule, the capsule will be open 100 years from now. So this will be presented at the Vienna conference, showing or closing, locking that closet with items of what we've been doing, books, models, maybe like a drill rig behind you, Jason, or the Casagrande tool, to show 100 years from now what we've been doing in the past 100 years. I will not be alive, maybe you will, but that's an exciting project also by ISSMGE. I wish you all a wonderful week and hope to see you all very soon. Thank you so much. Bye-bye.
Yes, thank you all.